Alright, hey, I wanted to go over some details on the Class 5 homework, and I don't want to spend too much time in class tomorrow going over these, so I thought I'd put them together in a video. Just some general comments. Looks like people have the right basic idea, but a few details. So, question 1 wanted you to draw a stack and perform some pushes and pops. It wanted you to do push 10, and then a push 20, and then a pop, and a push 10, and then 3 pops. And it said to use an abstract stack, but you can use the stack that we're learning about for the PIC processor. My main comment here is that when you're asked to do a question like this, the question actually said, show the stack pointer, and the location of top of stack after each instruction. It's really helpful to actually draw a new copy of the stack each time that an operation is performed. So for answering this question, you could say something like, initial setup, and here's your stack, and location 0 we know doesn't have anything in it, and stack pointer equals 0, and top of stack. Since the stack's empty, top of stack doesn't really make sense. It could be 0, it could be not applicable, it could be undefined. We'll just call it 0, but I'll put it in parentheses. And top of stack, is pointing here at location 0. And then we could put another section and say after push 10, and now we could show the stack and say what does it look like. So here's location 0, 1, 2. And we know that we're going to put a 10 down here. Stack pointer is going to be equal to 1. Top of stack is going to be equal to 10. And it's going to be pointing right here. And then we could add a third copy and say after push 20, and show our stack again. Here's our 10. This time our stack pointer is going to be 2. Top of stack's going to be equal to the thing that we pushed at location 2, and there's where top of stack is. And then after the pop, what changes? Well, the stack pointer gets decremented, so that's equal to 1, and top of stack is now pointing to location 1 in the stack, which has a 10. Notice that this 20 is still sitting in the stack, but we're basically saying we don't care about it. The stack ends with this 10, so anything up here is not part of the stack. So yeah, it's useful to write out the stack after each instruction so that you can clearly see not just, a sequence of stack pointers and top of stack, but also where those numbers are coming from, how the stack is actually laid out. So when you see questions on an exam, for example, that says show the stack after each instruction, go ahead and draw it out. Take that extra time to do that. The next thing I wanted to talk about was this question, for example, like questions 3 and 4, where it wants the address of each instruction in program memory. So question 3, you were given a set of code like this, and it asked how many bytes does each instruction require. That you just get from the data sheet, right? You look in the data sheet, table 20-1, and most instructions are 2 bytes. Call, go to, and move FF are exceptions. They take 4 bytes. Most other instructions take 2. So I put down, 4 bytes for the call, 2 for the increment and return. Org, sub, they are not instructions, right? Those are assembler directives. So they don't actually take any space in program memory. They're things that the assembler looks at, deals with, and then tosses aside. So when we end up with our program in the program memory, call sub will actually say call 100 hex. Because the assembler will look at sub and say, okay, so sub goes with this instruction, which is at location 100, because I saw an org statement. And so it'll store call 100 hex in the program memory. Alright, so how do you figure out the address of each instruction? We're not executing the code, we're assembling the code. We're saying, hey, let's take this code and put it into program memory so that it can be executed, but we're not executing it. So the fact that this is a call to down here does not change where this instruction is stored in memory. The only thing that matters is we said org 80, which means the next instruction gets stored at location 80. So call sub goes at location 80. But remember, you know, everything is sort of byte oriented. The program memory, if we think of it as a series of bytes, so that each of these entries is 8 bits, which is 1 byte, then the call instruction starts getting stored at location 80, but it takes how many? 4 bytes. 1, 2, 3, 4. So call actually sits between 80 and 83. And then if there was an instruction after call, that would go at 84. Alright, when we get to increment 80, that's stored at location 100. Why? Because we said origin 100. So incf gets stored at 100. It takes 2 bytes, so it sits in 100 and 101. And then the next instruction, return, well, there's no org statement, so it just goes in the next available spot. Incf is in 100 and 101, the next spot is 102, and return takes 2 bytes, so it goes in 102 and 103. And then if we had another instruction after return, that would go at starting at 104. So when you're trying to map these things into memory, right, make yourself a memory map and make this mental connection between the instructions, how long they are, how many bytes they take, and where they sit in memory. And that's a useful connection to have. So then later on, there was a question that looked like this: org 0x40 increment x20 push pop. Oh, and by the way, the fact that this increments file register 80, nothing to do with this 80 up here, right? This is a file register address. This is an address in program memory. So remember, the PIC has 2 separate memories: program memory for instructions, file registers, or data memory for data. Alright, so how do we do this problem? Well, again, we have to figure out where each instruction sits in memory. So origin 40 does not take any place in memory, but it says the next instruction goes at location 40. So this sits at location 40. This takes 2 bytes, so it's actually stored at 40 and 41. This push is at 42. This push is at 44. And this push will be at, this pop will be at 46. And so here again, the question said to show the stack pointer on top of stack after each instruction. So we could say, you know, initial and the stack's empty. Stack pointer equals 0. Top of stack, we'll just say it's equal to 0. This is also what things look like after the increment file, because inc file does not affect the stack. The only things that really affect the stack are mostly call and return, push and pop, or anything similar to that. There's a return from interrupt retfeed that also touches the stack. But increment, add WL, move LW, swap F, none of those affect the stack. The stack is only used basically for saving information that we want to get back to in reverse order later, so like a call return situation, or this peculiar push pop. So increment doesn't change the stack, but when we say push, what does it do? Push says push address of next instruction. And when we say next instruction, right, if this was the call that we're making, we know the call saves the address of the next instruction. We don't mean this increment down here at 100. We mean the next instruction in program memory, the instruction that's stored starting right here, which we know is at location 84. So when we execute the program, the next instruction to be executed will be this increment down here. But that's not what the processor looks at, right? The processor says, hey, I'm doing a call. I'm going to store the address of the instruction that comes after this in program memory. It's a bookmark, right? It's trying to remember what was it going to do next. so that when you say return, it goes back to what it was going to do next. And what it was going to do next after this call was whatever comes at location 84. Now the call is weird because it jumps down somewhere else, but if we just look at a series of instructions, the thing that comes after the call is whatever this next instruction is at 84. Alright, a little less confusing with push and pop. Push, just push the address of the next instruction. In this case it's 44, and so we could say after push our stack looks like this. Stack pointer gets incremented, top of stack points right here, and it's going to be equal to whatever was pushed on the stack, which was this hex 44. So top of stack equals hex 44. And then after the second push, we'd have a 44 and a 46, and the stack pointer would be 2. Alright, so most people had the right idea here. This is just a few details. The other thing I wanted to talk about was questions 7 through 11, the interrupt code. And you'll get more practice with this as you work on future labs and as we get into other types of interrupts. But here's the basic deal, right? So question 7, you wanted to write code that basically copied from file register 2 to port A in a loop. So we could do something like move LW 7F, move WF, add con 1, and then there was a loop. And we want to copy file register 2 to port A, so we could say something like move F 02, 0, and then move WF port A. Oh, and we also got to clear the tris A register, so we could say clear F tris A. Port A is all outputs. And then this says copy, and I'm going to use angle brackets here to say the contents of file register 2 to W, and then copy W to port A. And question 8 said, what if you want to move this to location 20? So we could say origin 20 and put this code here. But the trick here is when you start executing your program, it always starts from the instruction at location 0. So at location 0, I'm going to put a goto statement. I'm going to say go to main, and up here I'm going to label my first instruction main. So now when I run my program, what happens? It starts at location 0, it says go to main. Main is down here, it'll clear my tri-state register, set up addcon 1, go into my loop. But what I've done is I've freed all of these memory locations up here between location 4 and location 20. And that's important because of this notion of interrupts. And when an interrupt occurs, the CPU is going to jump to a particular location, either location 8 or location 18. So let me put my go-to loop here. So questions 9 through 11, well mainly 9 through 10, want you to set things up so that when you get an int 0 interrupt, we will increment file register 2. So this loop's always copying the same value to port A. If file register 2 has a 17 in it, port A is always 17. But we want to set things up so that even though we're in an infinite loop here, if we trigger this int 0, which we can do by hitting pin 8 on the outside of the PIC processor, if we trigger int 0, suddenly port A would be outputting 18 instead of 17. So that's the idea of an interrupt. We have an infinite loop, but we can still cause something different to happen. So let's take a look at how we go about setting up that kind of interrupt behavior. Alright, so let's look at this interrupt code in more detail. And we've gone over this already in the video, but let me look at it specific to this set of questions from class 5. We want to enable interrupts on int 0. So int 0 is, this pin 8 on the pick processor, it comes in on RB0. So we need to do a few things to set up interrupts, and this would all go, you know, kind of inside here. Set up the interrupt system. So let me hop over to a separate page for that, and let me say, you know, set up the interrupt system. Well, first thing we have to do is we have to say, hey, we're going to send information in on this pin, right? We're going to apply a voltage here, and that's going to generate an interrupt. In order for that signal to get into the chip, we've got to say RB0 is an input. So we need bit 0 of tris_b to be a 1 for input. So we've learned about bit operations. I can do this the sort of fancy way. I can say bit set file, and I'll say tris_b, comma 0. And this says tris_b bit 0 is a 1, so port B0 is an input. Right? So bit 0 of port B, that's RB0, that's this pin right here. So now pin 8 is set up to receive information from outside the chip. So that's the first thing we have to do. And if you don't do that, none of the rest of this works. Super frustrating. So set up tris_b bit 0 to be a 1. Remember, 1 means input. If we made it a 0, it would be an output. Alright, next thing we have to do is enable interrupt priorities. Now we don't really need to do this, but it's like ADCON 1. We're just going to do this most of the time that we're dealing with interrupts. We're going to set up the system to say, hey, I want 2 different types of interrupts, high priority and low priority. And we do this by setting up a bit in the ARCON register. So if we come down to ARCON, bit 7, that's the priority enable. If we set this bit to a 1, it enables priority levels on interrupts. And we're just gonna do that all the time. So we can say bit set file ARCON, comma, and I could put in a 7 here because I know it's bit 7, but I can also use this label IPEN. And IPEN is defined in our include file to be the value 7. So I'm going to say bit set file ARCON, comma, IPEN, just like this. And this says set ARCON bit 7 to 1, which means allow priority levels. Alright, so now the system understands high and low priority interrupts. Next thing we're going to do is enable int 0 interrupts. Lots of things can interrupt the system. Int 0, int 1, int 2, a change on port B, a timer expiring. Lots of different things can cause interrupts. But by default, none of them will. They're all disabled. So we're going to say, let's have int 0 be something that's allowed to interrupt us. And so all of these things, it's a matter of looking through this data sheet of interrupt registers and trying to figure out which bits you need to set. Well, we need this bit int 0IE, that's the interrupt enable bit. And if this bit is set to a 1, it enables int 0 to act as an interrupt. So this is going to be another bit set operation. I'm going to say bit set file. The name of the register is intcon. And the bit, well, we could just say bit 4. But again, let's avoid magic numbers. Why is it a 4? Maybe it's supposed to be a 3 and I typoed. Let's call it int 0IE. And that include file will set int 0IE to be the number 4. So I'm going to say bit set file intcon, comma, int 0IE. So that enables those interrupts to happen. There's a number of other things we can set up with int 0. For example, we could set up the priority, the edge for int 0. We could say, should it interrupt on a rising edge or a falling edge? The default value is a 1. That's what this little 1 tells me right here. And 1 says interrupt on the rising edge, which is what we want. We want it so when we put 5 volts instead of 0 volts, that causes an interrupt. So we don't have to set that. If we play with other interrupts like int1 and int2, we can set up their priority levels right here, make them high or low priority. Int0 is always high priority, so we're not going to have to worry about that. And then the last thing we need to do is enable high priority interrupts. So what have we done? We've set up this pin to be an input pin. We've said we want priority levels on our interrupts. We've said we want int0 to be able to generate an interrupt, but nothing is going to interrupt the system until we say allow high priority interrupts or allow low priority interrupts. There's like a global enable. And that global enable is, in this case, bit 7 of intcon, and it's global interrupt enable high. Right? It's not GIE, it's GIEH, global interrupt enable high. And if we want to do low priority interrupts, we say global interrupt enable low. So here we're going to say one more bit set file, intcon, comma, global interrupt enable H. And this says allow high priority interrupts. If we wanted to allow low priority interrupts, we could also set GIEL. And then low priority devices like maybe int1 and int2 could also generate interrupts. Alright, so this is all of our setup that goes up here, and after we do this instruction, if there's a rising edge on pin 8 of the chip, it will generate an interrupt. And so the last thing we have to do is say what should happen when an interrupt occurs. Well, the system, the CPU, when it sees a high priority interrupt, it will jump to location 8. And that's the only thing the interrupt does. Basically, it jumps to location 8, but it does it with a call statement. So the instruction it was about to execute, the address of that instruction gets pushed on the stack. And instead, it jumps to location 8. We handle the interrupt however we want to, and when we're done, we'll say something like return, which will go back to where the processor was when it got interrupted. So somewhere in our program, it doesn't have to go up here, it could go down here, it could go anywhere, but somewhere in our program we need to say origin 8, and this is our high priority interrupt code. And if we're only doing a few things, we can put the instructions right here. But you know, if we put our main program at 20, we've only got a certain number of spots between location 8 and 20. So what you typically see in our code is just like up here where we said at location 0 go to main. Down here I could say go to high priority handler. And then down here in my code I could put something like high pri, and I could list my high priority interrupt code there. Alright, so let's just look at that interrupt handling code. So down here at our high priority code, what do we have to do? Well, what we want to do is this business of when the interrupt occurs, increment file register 2. So we could say increment file register 2. So that when we go back to our main program, which is copying from the file register to port A, the value on port A magically increases. But we also need to do a return to get back to where we were when the interrupt occurred. But we also need to do one more thing. We need to clear the interrupt request. So clear the int0 interrupt request. Well, what's this about? When something requests an interrupt like int0, it sets a flip-flop, it sets a flag. And that flag is what eventually causes the processor to go to location 8. We are responsible for clearing that flag. Otherwise, when we return from the interrupt, the CPU will check that flag and say, hey, someone's trying to interrupt us, and it'll jump back to location 8. So we've got to clear this interrupt request flag. And that we can take care of in the intcon register this bit right here, int 0if. That's the external interrupt flag bit. And if we set it to a 0, it'll say there's no interrupt occurring. If it's equal to a 1, it means an interrupt occurred, and it says must be cleared in software. So how are we going to do this? We're going to say bit clear file int con. And again, I don't want to just code the number 1, even though it is bit 1. I'm going to use the symbolic name int 0if. So this is the instruction that clears that interrupt request. And then we have to do a return. But the one other thing we have to do is we have to re-enable interrupts, because interrupts are disabled once an interrupt occurs. So we enabled them originally, but when an interrupt takes place, interrupts are temporarily disabled. So we need to re-enable them and we need to return. But we want to do that in one instruction, so there's a special instruction for that called retfee. And this says enable int and return to where we were. And so that's our whole interrupt handler. So those are the pieces that go together into these last few questions. And the suggestion for 9 was to not use bit-oriented instructions. So if we wanted to set intcon, for example, to have int 0ie and have this gieh both turned on to 1, what we would need to do is look at the intcon register and say, okay, we want a 1 here and we want a 1 here. And so this looks like 1001, 0000. We'd move a 90 hex into W, move W into intcon, and that would set that register up. And that's just, you know, to get some practice looking at the register and thinking about how all these bits interact. But then question 10 says go ahead and use bit-oriented instructions, so bit set, bit clear, and so on. Go ahead and use those and make your code easier to understand and easier to write and less prone to bugs. Anytime we have magic numbers like, you know, let's move 90 hex into intcon, maybe I messed up. Maybe I you know, wanted to move 90 hex, but when I converted 1001, maybe I wrote it as, you know, 80 hex. And that's a bug you're never going to find. It's really hard to debug that kind of thing, because you stare at your code and you think you know what it's doing, and maybe you wrote some comments saying what it's doing, and unless you go back to the data sheet and recheck every instruction, pretty hard to find. So that's why we want to try to use these symbolic names. If we want to turn on timer 0 interrupt enable, we'll say TMR0IE, and the register will be intcon instead of, you know, some 3-digit hex number, and it minimizes the chance of bugs. Alright, so that's the basic setup for interrupts. Let's just go ahead and pop that into MPLab, and let's see what it looks like in action. Alright, so let's go ahead and run this in MPLab, and I'll just start with some boilerplate code I have here. So origin 0, I'm going to say go to main, and at origin 8, I'm going to say go to high priority interrupt. I'll camel case this. Go to high priority interrupt, and then at origin 20, this is where I'll put my main program. Alright, so org 0, that's always where our program starts. So CPU always starts here. Location 8, this is the high priority location. Sometimes we call it the high priority vector, and we say the CPU vectors to that location. Fancy way of saying it jumps to that location. So that's where we end up when there's a high priority interrupt, and we'll go down to high pri int. So our main program, let's go ahead and set that up. So initialize the I/O system. So move 0x7f and move WF. Add con 1. And then we said we wanted to make sure bit 0 of port B was an input. So we'll say bit set file tris B, comma 0. Set RB0 as an input. Alright. So let's enable interrupt priority levels. So bit set rcon, comma ipen. And I'll throw some extra spaces here. Enable int 0 interrupts. So this is also an int con, comma int 0 interrupt enable. And then turn on global high priority interrupts. So we'll say bit set int con, comma global interrupt enable high. And I'll put a comment here after this. Interrupts are live. Alright, so here I'm going to place my loop, which says move 0x02 into the W register, and then move WF to port A. Oh, we also want port A to be outputs. So let's set up port A to be outputs. So we'll say clear file register tris A. So port A is all output bits. And so our main loop is sitting here, and we're just looping forever. Take file register 2, copy it to port A. And I'll add a watch in here for file register 2, just for fun. We'll bring the value over here. Alright, so we're all set except for this business of what happens when an interrupt occurs. We're going to go to this high pri int. So let's put this down here. So here's our high priority interrupt. Now, we don't care where this is in program memory, right? It's going to be somewhere after, you know, this was location 20. We've got all of these instructions here. We've got our loop. We don't really care what the address of this is, because when we get an interrupt and we go to location 8, it's going to say go to high pri int. Wherever that is, that's where it's going to jump to. Alright, so what do we do in our high priority interrupt routine? Well, first thing we do is we increment file register 2. This is the main goal. And then we have to disable that interrupt request flag. We have to turn it off. So we'll say bit clear file int con int 0 interrupt flag. So we turn off the interrupt request bit, and then we're going to do our ret fee. So re-enable ints and return to where we were. And where were we? Well, we were probably somewhere in this loop right here, which, by the way, should end with go to loop. So we're probably somewhere here, right? This is copying file register 2 to port A. And then an interrupt occurs. We're going to jump to location 8. That's going to bring us down to high pri. We're going to increment file register 2, turn off the interrupt request bit, and then return from the interrupt, which will take us back to our loop up here. Alright, so there's our program. Let's go ahead and stick a breakpoint right here, and let's go ahead and run this in the debugger. So it's executing. We're sitting at this breakpoint right here, and I'm going to add a pin here for int 0. And my action is going to be pulse high. So pulse high means when I fire this, the pin will go high for a brief instant and then go low again. And so it's going to indicate the request from outside for an interrupt on that int 0 pin. So let's start stepping through our simulation and let's look at our variables. This moved on me. So file register 2 is a 0, port A is a 0. Let's start set up addcon 1, set up RB0 as an input, port A is output, enable priority levels, enable interrupt 0 interrupts, enable global high priority interrupts, and now we just loop. And you know, not very exciting, we're just copying a 0 to port A, so port A is 0. But let's go ahead and fire this interrupt. And when the interrupt fires, what happens? We do one more instruction and suddenly we jump to location 8. And at location 8 it says go to high priority int. So we jump down here, we increment file register 2, so now this is a 1. We do the return from interrupt and we go back into our loop. And so the next time we loop, we copy from file register 2 to the W register, and then we copy that to port A. Port A became a 1. And now we're just sitting here looping forever. And if we fire an interrupt, we'll go a couple more instructions, come down here, do the same thing, and now port A is a 2. So that's the whole nature of interrupt-driven code. We look at the code, it's just an infinite loop. It's never going to do anything except, you know, copy from register 2 to port A. Not true, right? Because we've set up an event handler. We've said, hey, while you're running, if something happens and you get an interrupt request on int 0, do something different. Jump down to location 8 and then follow the instructions there. Come down here, increment file register 2, clear the interrupt request, go back, keep going. Alright, that's interrupt driven code. If we add a watch for stack pointer and add a watch for top of stack low, we can watch these and let's see what happens when we get an interrupt request. So we're just sitting here spinning. We'll fire the interrupt request. And at this point, two things happened. First of all, the stack pointer went to 1, and second, the top of stack went to 2E. Okay, what is 2E? Well, let's go ahead and take a look at the disassembly listing. And if we find location 2E, that's the top of our loop. That's this movef instruction, right? That's stored in program memory 2E. That's where it was about to execute. So this 2E that's sitting on the top of the stack indicates that, hey, we were about to perform this move instruction, and we got interrupted. So we're going to go ahead, we're going to do what we want to do in the interrupt, clear the interrupt, and then we're going to do a retfee. And when retfee happens, two things are going to happen. One, the stack pointer is going to change to a 0, and our program counter, which we can see up here, should change to 2E. So we go ahead and we execute the retfee. Stack pointer is 0, program counter is 2E, and the green bar says we're about to execute this move F instruction, which is the instruction stored at location 2E. So it basically did a subroutine call when the interrupt happened. Processed the interrupt, went back to where it was, and now we're continuing this loop as if nothing had happened. Alright, and a couple of things to since we've got this set up here already, let's just play with a couple of things. If we don't clear this interrupt flag, let's go ahead and debug this. So we can start running, and we're sitting in our loop, and let's fire an interrupt again. And so we jump down to a high priority int, we increment file register, we do a retfee, so you know, port file register 2 got incremented to a 1. We return from the interrupt, and we execute. We find that we're right back in our high priority code, and we're going to increment file register 2 again, and we return from the interrupt, and we're back at this, vector location 8, which says go ahead and run the high priority interrupt code, and we increment to a 3 and a 4 and a 5 and a 6, and we're thrashing here, right? We go ahead, we process the interrupt, but as soon as we return, we immediately get interrupted again. And why is that happening? It's happening because when the interrupt was made, when the interrupt request was made, this bit in 0IF got turned on. And as long as that's turned on, the system thinks we're getting an interrupt. So we have to clear that bit manually in order to disable the interrupt request. So we have to put that clear in there. And then once that's in place, we can run our code. And if an interrupt comes in, we will get interrupted, process it, and then go back. And we won't get another interrupt until that action occurs again. So you can make yourself code like this and play around with it and sort of explore what these things actually do, right? As they say, don't take my word for it. Try it and experiment with it. All right, that's all I got. Thanks.